zone.
And what route are you in? Getting on
Pod side.
Alphabet. Where's the alphabet?
What is alphabet?
Why are you asking us?
All right, if you get slide 133
Yes.
in the slideshow, slide 133, there's several links there. One is to that another copy of this quiz that I've given you. Okay, that's there, but also these two handouts right here. All right, so these are steps for drawing Lewis dot structures for covalent compounds, also known as molecules. That's the step-by-step procedure that we're going to follow. And this is a list, a table of information that you're going to have to learn. Okay.
We have to memorize.
Yes, down through this row right here. The rest of it will be for next year.
So stop at 5.
Stop it after 4.
Oh, yeah.
Talk about why here in a bit. All right, so if you look at that handout I gave you, there's 4 compounds there listed: methane, water, ammonia, carbon dioxide. Okay. So first thing that you're going to be asked to do on the quiz is tell the formula for each one of those. So what's the formula for methane?
Is that an alcohol?
Hydrocarbon.
All right, yeah, right.
Yeah.
Snap.
You have to remember everything.
Oh,
Can't forget stuff in here.
Water is H2O.
Water's H2O.
Yeah.
Very good.
CO2.
How about
Not like
ammonia?
your TV show.
NH.
Oh,
4 plus?
That's ammonium. Ammonia. No.
pH.
Where did you get that from? I was talking about H2O.
Oh, 3.
Ammonia's NH3.
I feel like I've heard that
Yeah, I think I've heard that before.
before. Okay.
How about carbon dioxide? Oh,
CO2.
much better. CO2. Okay,
Yeah.
so we got to know the formula. So the first thing you have to be able to do, the reason we just spent an entire unit learning names and formulas is because we got to know the formulas and stuff, or we can't draw structures of them or do any much of anything else with them if we don't know which and how many atoms are in the molecule. Does that make sense?
Right.
We got to know which atoms and how many of each one are in the molecule. So that's nomenclature. All right, what's the next thing on the list?
Lewis structure.
Lewis structure. Okay, that takes us to handout number 1 right there on the board. Here are the steps for drawing Lewis dot structures for covalent compounds. Number 1, we're going to add up all the valence electrons. So we're going to go across each 4 of these. We're going to do step number 1 for each of those 4. And step number 2, 3, and get to the end, we'll have 4 structures completed. All right, step number 1, add up all the valence electrons in the molecule. Now, valence electrons are not the same as the total. If we remember from the other day, valence electrons are 1, 2, 8, 7, 6, 5, 4, 3, right? Okay. So how many total valence electrons in a molecule that has a carbon and 4 hydrogens?
4 and 1 to 5.
There's 4 hydrogens.
Oh, so 8.
8. So there's 4 in the carbon, and 1 in each of the 4 hydrogens will make 8, right? We're good with that?
Wait, can you repeat that, please?
I'll just a second. Let's make a little note of it right here. 8 electrons. So there's 4 valence electrons in the carbon. Everybody needs a periodic table, by the way. This won't make any sense at all. Okay. So this is the periodic table. There's 4 valence electrons in the carbon. Each hydrogen has 1. There's 4 hydrogens, right? So 4 plus 1 plus 1 plus 1 plus 1 is 8.
Okay.
Got it?
Yeah.
All right.
Oh, yeah.
How about water? I mean, is it going to have 8? 6 plus 1 plus 1, right? That's 8. How about ammonia?
8.
8. Very good. 5 plus 1 plus 1 plus 1.
Oh, I'm getting what you're putting there.
There we go. I'll give you a hint. The next one's not 8. How many are in carbon dioxide? 16, right? 4 plus 6 plus 6. Okay. 4 plus 6 plus 6 more would be 16. All right, so we need to know that. That's the first thing we've got to know before we can draw a Lewis dot structure for a molecule. We've got to know how many electrons are in it. Valence electrons specifically. Step number 2, place a single bond between each atom. Remembering 2 things in this order. Hydrogen is always terminal. What does it mean to be terminal?
Last.
Last, at the end, on the outside, not in the middle, okay? All right? The central atom should be the least electronegative, so that really doesn't matter if you've got two atoms and one of them's hydrogen and the other one has to go in the middle, because hydrogen cannot go in the middle. But if you have two atoms that are neither hydrogen, how you going to know who goes in the middle? We'll put the least electronegative one in the middle. So we'll see how that works in a second. Jot this down about hydrogen. Okay? Hydrogen can only have a single bond. No doubles, no triples, and no lone pairs on a hydrogen. Hydrogen is going to only have a single bond. So if we're going to single bond everything together and hydrogen can't be in the middle, then we're going to put carbon in the middle. And we're going to put the four hydrogens single bonded to the carbon. Put it around the carbon in a nice, evenly spaced type manner. Here we're going to put oxygen in the middle. Hydrogens are terminal. This one we're going to put nitrogen in the middle because it's not hydrogen. Just catch up there for a second. Carbon dioxide doesn't have any hydrogen in it, correct?
Correct.
So this is going to go in the middle. Carbon. So the most electronegative element of all is fluorine. Oxygen's number 2, chlorine's number 3. So oxygen is the most, carbon's got to be the least in this compound, so it goes in the middle. And we're single bonding it because everything has to be at least single bonded or it's not bonded at all. Right? It might end up later on being double or triple bonded. We might have lone pairs here in a minute. We'll have a lot of things, but at a minimum, the atoms have to be single bonded. So that was step 2. We placed a single bond between each atom. We made sure hydrogen was not in the middle. And if we didn't have a hydrogen, we made sure the least electronegative thing was not. Like that so far. Step number 3. We're going to add lone pairs for all of our valence electrons are accounted for. So we added this up for a reason earlier, okay? This has to have 8 electrons in the diagram. But it's got 2, 4, 6, 8, so that's good, right? Okay. This one's also got to have 8, but it only showing how many? 4, 2, 4. So we got to put lone pairs, number 5, 6, 7, 8, like that. Don't put them on the hydrogen because they can't go on the hydrogen. How many are showing on this one right now?
6.
6. How many should there be there?
8.
8. So we're going to put 2 right there. Don't put them on the hydrogen. This needs 16, but right now only has how many?
4.
4. Okay. Here it would be best. You'll end up moving stuff around less in if you put them on the most electronegative. So that's 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yep.
Wait, what's the reason why we're putting the dots where they are?
We're putting them because we got to have 16 electrons. And we're putting them where we put them. It doesn't really matter because we're going to move them around anyway, but you'll end up moving less of them if you put them on the most electronegative. So oxygen being electronegative means having strong attraction for electrons, which means that it's most likely where they're going to end up. We may end up moving to something else, but probably not. If you put them, it doesn't really matter because you'll move them, but you just end up having to move a lot more stuff. Kind of a shortcut. Go ahead and put them on the most electronegative. Step number 4, we're going to check the octet rule, which means everybody wants 8, except for hydrogen and helium, but hydrogen is the one that matters here. It's called the duet rule. Hydrogen only needs 2. Everybody else wants 8. So we're going to check that, okay? So we look right here. This carbon, when we have this drawn, has 2, 4, 6, 8 electrons. Check, right? 2 for this hydrogen, the 2 for this one, the 2 for this one, the 2 for that one. Check, okay? This oxygen's got 2, 4, 6, 8. Each hydrogen has 2. That's good. This nitrogen's got 2, 4, 6, 8. Each hydrogen has 2. That's good. That means that these three, these are our final answers right there with those three. What's the problem here? Or is there a problem? Does that oxygen have 8 electrons?
Yes.
How about that one?
Yeah.
How about that carbon?
No.
No, that's wrong, right? So carbon's got to have 8 electrons, but it doesn't, right? So if it doesn't, okay, if it's good, you skip step 5, and we're going to be skipping step 6. We'll save that for next year, okay? So in other words, if you check the octet rule in step 4 and it's good, then you're done, final answer, okay? If not, then you got to go to step 5, which says convert lone pairs to double or triple bonds. So we're going to take a lone pair off of this oxygen and make it a double bond. We can't add or remove electrons. We can move them around. You got to have 16. We don't get to take 2 off or just make up 2. But we can take 2 and move them. So we took a lone pair and made them a shared pair. That made carbon have 6 instead of 4, so we're getting better. Let's take 2 off of this side and put them right there. Now everybody has 8. Well, so that's the Lewis dot structure of carbon dioxide, ammonia, water, methane. Okay, row 2 on your quiz. Good with it. Got your lone pairs in the right place. All right, what's the next thing on there?
Geometry.
Geometry. Okay, if you look at this chart over here, there are 2 geometries. There's electronic geometry and there's molecular geometry. When chemists just say geometry, like that quiz does, they mean molecular geometry. Okay? All right, so the quiz is asking for molecular geometry. The test later on, next Thursday, November 2nd, will ask you for either one. So what in the world's the difference? There's my little model though. So electronic geometry, can we jot this down right quick? Electronic geometry is the arrangement of regions of electron density. Okay? It's basically the arrangement of the electrons. The molecular geometry is the arrangement of the atoms. Sometimes they're the same, a lot of times they're not. What we're going to learn to do here, very simple thing, is we're going to count the regions of electron density. The AP exam likes to call them electron domains. But regions of electron density is what it was called forever. So what is a region of electron density? It's either a single bond, double bond, triple bond, or a lone pair. Pretty simple thing to count, okay? It's either single bond, double bond, triple bond, or a lone pair. One thing that people get confused about is that, like, for example, a double bond is one region of density. Okay, triple bond is one region of density. It's not 3. So if we look right here, methane has 1, 2, 3, 4 regions of density around the central atom. We're always counting around that central atom. Water, around the oxygen, 1, 2, 3, 4 regions. Around this nitrogen, 1, 2, 3, 4. Around this carbon, 2. Okay, this is 1, that's 1. The lone pairs are not on the carbons, they don't count. All right, so what are we counting for? Well, we've got this little chart, okay, that we're going to put to memory over the next week or so. And we're looking for regions of density and how many lone pairs there are. So if we look at methane, it has 4 regions and no lone pairs, so 4, 0. All right, that's what we call a tetrahedral. This is what a tetrahedral looks like. So the reason we've got to learn all this is that we're going to draw these 2-dimensional structures. Everybody know what I mean by 2-dimensional? It's just got height and width. Okay, there's no depth to these drawings. All right, So we're gonna draw those things, but that's not really what methane looks like. Methane really looks like this shape, three-dimensional structure, okay? So we gotta be able to draw that, look at that on paper, but see this in our head. It's one of the tricks of chemistry, okay? Not the easiest thing to do. It's easier for some people than others, okay? But you've got to get to where when you look at that, this is what you're really seeing and thinking. Okay? This is a tetrahedral, which is simply a geometric term for a central object that has four things around it. And those four things are spread out from each other as far as they can get. Okay?
Is that like 30?
1, 2,
Oh,
3, 4.
wow. I was like, I really thought that was 3. Like I was like, but up there it's 4. Oh snap. That's bad. I
It
really
is.
thought that
It's
was 4.
bad. I like to say that if you can count to 8, probably make at least a C or B in chemistry. You know, you have to count to like 10 or 12. You have to get 8 students. So I don't know if you're gonna make it.
I really I was looking so hard. I really thought that was 3. That's it. So like,
We always say that like basketball officials are the dumbest because they don't have to count anything. Baseball officials have to count to 3. Football officials are the smartest. We have to count to 11.
what do you have to count?
And the players count to 11, but that's the max, right?
Right.
I always tell people to get confused. If you count to 11, you find yourself confused. There's probably more than 11 people. Okay. Baseball guys just got to count to 3. Well, 4 if you count wrong. I guess it has to count to 4. Basketball guy doesn't count anything.
I mean, they gotta count the free throws on this shot.
Bookkeeper keeps up with that. Basketball people are so dumb, they got a person over there writing on that for them. Kind of like that chemistry. You count to 8.
I was looking at baseball.
But you only made it to 3, and you started to struggle after that. So I don't know. All right. Now, this little shape, the tetrahedral, one thing in the middle, 4 things around it. Okay. The electron pairs, 2 here, 2 here, 2 here, 2 there. They don't like each other. Okay. So that makes this thing spread out.
Like I can
The way he's holding
Hide
it.
one from you. Turn this.
And I still see 3.
Because your head's.
Why don't you give it to him?
Yeah, let him hold it.
Feel it.
Find them.
Okay.
He's a hands-on.
Oh. Okay. I got it. I made
You know.
it. It's 4. Okay.
All right.
Almost got 3 again.
Alright.
Anybody else need to count? You can see the 4 dots.
I trust
One black and one 4 green.
So like y'all, like it is, y'all saw 4.
you.
Okay,
Yeah,
yeah.
yeah.
Well, it's all 3 for a little bit, then he kept flipping it around, like, okay, it's 4.
What if I think I'm cooking right.
But you can still see shapes in the
You can still see the shapes. Yeah.
color.
Anyway,
Easy person from addition.
so carbon,
Screwed by it.
I'm sorry, methane has 4 regions of electron density. Okay, so that means it's a tetrahedral electronic geometry. The arrangement of the 4 electron groups is tetrahedral. Methane has no lone pairs, which means every one of these electron pairs is connected to an atom, in this case, hydrogen. Okay, so that means it's also molecularly tetrahedral. The arrangement of the 4 atoms is tetrahedral. Okay, it'll be different here on the next one. If we look at water, it's got 4 regions, but 2 of them are lone pairs. So if we look at our chart, 4, 2 is electronically tetrahedral. but it's molecularly, what does that say? Bent. Here's how that works, okay? All I took to a mall, so pay attention now. Get weird. 4 minus 2 is 2. Plus 2 plus 2 is 4. 4 minus 2 is 2. So, this is what water looks like. It has this bent structure, okay? It's bent, okay? But electronically, it's tetrahedral because you got these two lone pairs, okay? So electronically, tetrahedral is still the same, but molecularly, we just look at the atoms and we call that bent. Okay? Go back to the angles.
Is that because the two dots are on each other?
Above that. Triangle.
It's bent, right?
Uh-huh.
What?
And
So why is it bent?
the
Huh?
green
Because
dots,
these two are trying to get away from these two.
and the green dots
Yeah.
are hydrogen.
All right,
So the top two,
Triangle.
that's the lone pairs.
which are,
Those two pairs of dots.
yeah, that's what I was asking.
Right, okay. Yeah, so they're trying to get away from each other.
So when you, okay, yeah. So the next one, you will add a green dot.
So the next one's in between. It's got one lone pair and 3 atoms. So it's electronically still a tetrahedral, right? There's still 4 pairs of electrons, but there's 3 atoms, which means this is called trigonal pyramidal. Triangular base pyramid. Just sit it down like that. Looks like a pyramid. Triangular base.
Sorry.
I'm stupid.
Triangle.
All right. Now, here's a number we have to know. For a tetrahedral compound, how much time have I got? Good. All right, so for a tetrahedral compound, the bond angle, the angle between these two bonds, okay? Geometry class, right? You got point, 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 right? Lines lead at a point, line segments, whatever. There's an angle there. For tetrahedral, it's 109.5 degrees. You gotta know that number, okay? That's a very important number in all of nature, okay? Because carbon, a tetrahedral carbon makes 109.5 degree bond angle. That's sort of part of like the fine tuning of the universe. Like carbon molecules have those angles, and that makes the basis for organic chemistry and biochemistry and the fact that we're alive and stuff you're talking about it. Okay, if that's not 109.5 degrees, then nothing is what it is. So it would be something different. Now, if you take off one of these, if you look at 40, it says tetrahedral, tetrahedral, and then the bond angle is 109.5. What is it if you have one lone pair?
107.
107. So what happens if you look right here a second? Is the lone pair is more repulsive than the bonding pair. So when I take that off, these 3 guys down here are going to try to get away from that lone pair up here. So it's going to squeeze together. Okay, just a little bit. And it changes the bond angle by about 2.5 degrees. If you take another one off, it squeezes a little more. It squeezes about another 2.5 degrees. So water has a bond angle of 104.5. Okay. So we have filled out now Lewis dot structure for all 4 of them, right? Geometry and bond angle for the first 3. Correct?
Mhm.
We'll pick back up here. I would say tomorrow, but I'm not going to. So we'll pick back up here Wednesday.
Would,
Fill out the rest of it.
would carbon dioxide just be linear in the
It
180?
will be linear and
Where? Me, I would be there.
So like next Thursday, right?
Well, yeah.
Oh,
Next
no, it's
Thursday.
quiz.
Next Thursday or Wednesday. 'Cause we've got this Wednesday. So can I just copy that?
Don't copy.
The chart?
Yeah, it's almost 1:33.
Oh. Okay. But that, this is all the information that I need though, right?
Yeah,
Just fill it in.
theoretically, yeah.
Put it right there. Okay.
And when's our test?
Tuesday. Thursday, November
What's the
7th.
pine number?
This
You
quiz,
said
it's this Thursday, October 26th.
What is
Unit
that?
test is the next Thursday, November 2nd.
I will not be here November.
Yeah,
second.
That's
What's the November
One,
the second?
two, three, four.
Cross country sections.
the second, November 2nd.
I won't be here
1,
first
2.
either.
We have sectionals on.
Another study group, something in Monica.
Yes.
Another study group, okay. I feel like it is. Yeah, right?
Look,
Because listen, we pulled it up on like my TV screen and we connected my phone, or Patty's phone to it. So we had all the examples on the
Oh, it
screen
was
and we
so
walked
helpful.
through it.
It was so helpful, Mr. Fatal.
We
3.5
taught Sarah like
hours.
the entire lesson pretty much.
I learned so much chemistry in 3 hours. It was crazy.
And Sarah brought food
I went
too.
to a chemistry study group in high school one time. I didn't learn anything.
Sarah
My
brought
experience
crock
was very
pot.
different.
Me,
I
She
wasn't
brought
there to learn.
rice.
Because
We had
my
I
parents,
get there to
you
make
know,
down
my
the
parents,
emails.
Well, you know, my wife showed up. Obviously, we weren't married at the time. She was
Whoa.
in chemistry class.
High school
I'll let y'all figure out
sweethearts?
what she came there for, but-
Ah, she thought you was, Mr. Killer, you a killer.
Kind of a hint there. I took the hint. She showed up in a study group for a class that she wasn't even in.
Wow.
Oh, okay. Got it. Got it.
Hey, did you turn off the camera?
Nope.
So y'all high school sweethearts?
Yep.
Wow. We made it work.